So yeah, I will be talking more about sort of in sort of a way in which maybe we can make it easier to simulate circumgalactic medium and multi-phase gas in larger scale simulations. So from previous studies where we have looked at very small scale simulations where we are resolving the physical length scales and sort of we can capture the physics a bit better, it's been known that it's a very multi-scale problem. Dylan also showed a similar plot that I have on the right side where you have sort of clump size distribution and the smaller you go, the more clumps you start to see, and it keeps on going. Apparently, if you increase the resolution, you keep getting more and more of the small scale structure. So that sort of poses this problem if you are trying to do a larger scale simulation. For example, if you just want to simulate a galaxy, which is with the CGM, which is 10 kiloparsecs wide. From smaller scale simulations, we know that if you want to get the cold gas behavior correct, you might have to go up to sort of sub-parsec scales. You might have to resolve sub-parsec scales in the CGM, in the hot gas, and or you need your mass resolution to be very small to have converged behavior. And that poses an issue because then you have absurdly high number of grid cells. So it becomes very hard to do it in a larger scale scenario. But we know that these small scale effects can be quite important, not just in sort of smaller scale sense. It can be important at larger scales because they're a sort of integral part of how the baryon cycle works, and there are many observational signatures which depend on the smaller scale structures. So one solution to that is to have subgrid models which take care of these things which are happening at scales smaller than what you're resolving. So the roadmap that we have is we can take these idealized simulations that people have done before, including our group, and make a subgrid model out of it, which can then later be implemented into larger scale simulations and hope to have accurate representation of how the cold gas is behaving in the medium. So what we want to simulate now is a multi-phase gas. I don't really have to give this introduction here. The main thing I want to point out is the density contrast that we have. So it can be from 100 times to 1,000 times. Cold gas can be 100 to 1,000 times denser than hot gas, which is kind of close to what is the density contrast between water and air. And the good thing there is because water and air has a lot of, the interaction between them has an engineering application. And we can steal some methods from our engineering friends where they have come up with methods where you can keep track of multiple fluids in the same grid. And so they have been doing it for a long time where they have to work on this interaction between water, air, and any kind of liquid and like gas multi-phase situations. So what it essentially means is we have on a fixed grid, we don't have just one set of density, energy, and momenta. We have multiple. And how we keep track of what the different fluids are doing is via volume fraction. So for example, in this model, the one fluid would be the hot gas and the other would be the cold gas. And the volume fraction of the cold gas in a cell would range from 0 to 1 depending how filled it is. So the problem statement here is we want to go from these idealized high resolution simulations where we resolve the scales, and we want to run analogous low resolution simulations with the multi-fluid model. And they should give similar behavior. And we are using this ARIPO multi-fluid code, which was released, I think, earlier this year or last year by Rainer and Lars. So there are a few conditions to when we say that the model is working. Of course, we want it to work when the cloud is unresolved. So here I'm showing the cold gas mass fraction in each cell. It's just a slice. we, of course, wanted to work when it's unresolved, but we also wanted to work in resolved scales because you might, as the cold gas grows, you might end up in a scenario where your simulation is actually resolving the cold gas. We also want it to be resolution independent, so the model should not give you a different answer if the resolution is different. It should work for a range of Mach numbers. Should not. So this is turbulent Mach number. So the model should work not just for one. It just shouldn't be that you just happen to work for one Mach number and doesn't work for another. And it should be also work for different initializations of turbulence. So with those 4 conditions, we come up with we made the model. As I mentioned earlier, we have the hot gas fluid and the cold gas fluid, and there is mass, momenta, and energy exchange between them because of the multi-phase interaction. So, and we divide these 3 exchanges into 3 different origins. So one origin is through drag forces. Because your cold gas is moving through the hot gas, you get some drag between these 2, and that can exchange some momenta and energy. And similarly, you can destroy the cold gas and you can create the cold gas. And all of them sort of correspond to their own set of exchanges. Now, in a realistic scenario, all of them are working together, but for that to work, we have to make sure that each of them is actually correct. So we first start off with trying to test out without the cold gas creation. So this is essentially like turning off the cooling in the simulation. And we would call it adiabatic mixing in this case. So here on the left, I'm showing, so we use, for the high resolution idealized simulations, we are using Athena++. And on the left side is one of those cases. And I'm showing 2 2 simulations from our multi-fluid model, where in the middle one, we are actually resolving the cloud. And on the right one, the cloud is smaller than the grid cell. The main thing I want to show here is that we do see the cold gas being destroyed. The sizes are different. That's why the cold gas sort of hangs out a bit more here. But if we do it more quantitatively, we see that the dashed lines are what we want to match, and the solid lines are from the subgrid model, and they match pretty well. If we do a more extensive sort of test where we change those things that I talked about earlier, we change the resolution, we change the Mach number, we change the random initialization of turbulence, we find that the crosses, which are the subgrid models, they are in the agreeable region. They agree with the high resolution idealized simulations. So the main thing here is that I want to point out is that the cold gas destruction that we have in our model works well. Thank you. So I'll go a bit quickly. Now we go with the whole thing. We turn everything on, and with the cold gas creation, if the cloud is big enough, you can actually create more cold gas because it mixes, and you create more cold gas, and so on and so forth. So there we see. So this is from the multi-fluid model, and we see that we actually see the same thing. If the cloud is large enough, it grows. It matches very well the analytic solution that have been seen from previous small-scale simulations. And if it is small enough, it dries out. I'll go to the this is an example of a small-scale simulation. I'll go to the money plot. This is a comparison with the analytic simulation, and it's within the margin of errors. This is the money plot. So here we are trying to show the survival and destruction. On the right is again, oh, you cannot see the dividing line in this one. There's a dividing line here, just believe me. And it's the same one as this one, so you can compare that. So on the right, we have the small-scale simulations. These are, again, turbulent box simulations where you see destruction on one side and growth at one side. And if we do the same with subgrid models, and these have both resolved, unresolved, different Mach numbers, and everything, and we clearly see that both of them are agreeing with each other. So overall, what I wanted to show here was, again, if you turn on everything, we have the terms right, and it works. And it matches with the smaller scale simulations, even though we are not resolving the cold gas cloud. So what can we do with this? So we ran this sort of a test simulation to show that. And so we start off with 100 clouds, each of them smaller than the cell. And you can see that with time it grows. And to get this correct in a resolved sense, we would need 5,000 cells, while we are able to do it with just 64 cube. And with this subgrid model, hopefully in near future, we can run larger scale simulations where we don't have to go to sub-parsec scales. And with that, I will leave with my conclusions. Thank you.
Okay, we have time for a couple of quick questions.
It seems like if you compare it to the Subgrid Athena simulation, you seem to have slightly more distribution, even if the bulk cold mass looks the same. Do you know why that is?
Yes, so that's sort of because it's a projection, so you have a little bit of mass there. I am also showing the mass projection, so because the cold gas is much denser, so you end up seeing it just shows up as more. It's not really that different.
Yeah, actually, maybe just a clarification on this video on the right, lower right.
This one? Yes.
You're showing a volume which starts mostly hot by mass, and at the end it's all converted into cold.
It's not all. So we make sure that it's mass conserved. So it cannot happen that it be fully cold because the growth rate sort of drops down as you evacuate the hot gas.
But 99%.
Yeah, because the cold gas is very dense. It just looks like it's the most of the mass is in cold gases.
Yeah.
Yes.
Yeah. Can you zoom out? I mean, what are the implications of running such a model in a CDM?
So the idea would be then we can run the regular simulation, and you just have two fluids in the CGM. One is the hot gas and cold gas, and you can sort of track the cold gas as it goes up and then comes back down, while keeping the destruction and creation of cold gas physical in the whole thing. And you probably don't have to, because with the cold gas clouds, you need like 10 cells along the radius to get the destruction time correct or converged. But in this one, you don't have to. You're not sort of constrained by that anymore. This works.
Yeah, I think I missed something kind of basic, maybe, which is that in every cell you have a hot gas and a cold gas. What determines the temperature of hot and cold? Is that a choice you make, or is that imposed somehow by interactions with the environment?
So for the hot gas, we don't put it to anything. So it can evolve with turbulence heating it up or something else heating it up. For cold gas, we fix it at 10 to the power 4 in this case. Similar to what we also do in small scale simulations because of the temperature flow. But there is a scope where we can also make it vary. It's just that we wanted to compare it with small scale structures, so we skip. So there is a physical reason where it's the cooling curve, where the cooling is fast close to 10 to the power 4, so it just stays there. So yeah.
Okay, let's thank Kishore and other speakers.